So let's just start with a real quick review. All right, will you try this in your notes? The full and condensed electron configuration for molybdenum. Molybdenum, also known to basic sophomore people, molybdenum.
You can't just show a bunch of high schoolers work and expect them to pronounce it.
No, I know. I called it molybdenum probably for 2 or 3 years, but it's molybdenum.
Well, I hope you spell it
But
too.
everybody would know what you're talking about if you call them all over
The one that's AC, everyone calls it like Americanium, but it's Americium.
Go America.
Yep, exactly. Let's be us. Okay, I'm going to pause this. Condensed recording. Okay, we okay with that? Thumbs up. Okay. We have one last sliver of content. We started talking about it yesterday. Why are you not working? And it was this, right? So photoelectron spectroscopy. We'll flow through this. Axis of the graph. This isn't really like vocab, but these graphs are different than any graph you've seen. Do you know why? They're backwards. It's really dumb. I don't know why. Well, I guess I do, and it's fine, but I would prefer it was normal. So what we mean by that it's backwards, you have your number of electrons versus your binding energy, and it's like 1,000 here, and it's like 0.01 here. Usually in our lives, the small numbers here and the large numbers there. Okay, the reason why this is large is because it isn't like 100% true, but it's like the nucleus is here, and the ones that are close are the hardest to remove, and the ones that are a little bit farther, and then these that look familiar, all of you that watch the video. So it sort of makes sense, but just remember the axis is backwards in most things. Don't ask me. Huh? That is valid. Okay. Okay. Nuclear charge. This is actually coming up in chapter 7. Nuclear charge is known as ZEFF, but don't worry about that yet. Like, you're going to learn all about it starting on Monday. It's called the effective nuclear charge, but it's essentially, oh no. The nuclear charge is the positive charge from the protons. That's like all it is. So if it's lithium, it's element number 3. So the nuclear charge will be a +3. Easy enough. Now, what's that? It's the atomic number. Now, when we get to chapter 6, it's going to be a little bit different, but just where we are at chapter 6. I mean, chapter 7, we'll talk about it. But for now, in this application, it's just the number of protons that would go there. And then the electron, we usually just assume is 1 in this unit. Okay, fair enough. So here we go. You watched the video, so I'm going to go fast, but it's experimental technique to determine the relative energies of electrons in atoms or ions. So they energize it and they find out how much energy it takes to remove everything. And then by that, they can tell where those electrons were. Because if it was really hard, then they were really close. If it was pretty easy, then they were pretty far. Photoelectron spectroscopy, spectrometer, use radiation to remove electrons from an atom. Electrons are located in different energy shells. So valence electrons are easy to remove because they're on the outside. They have less attraction to the nucleus. And then core electrons are harder to remove because they're more attracted to the nucleus. All right, just in a nutshell, maybe someone's drawing, so I'll just put it here. So you have your nucleus, and then I'll just say all the core electrons are here. You okay with that? Then there's a valence electron right here. It is shielded from the positive pole here by the repulsion of these electrons there. Core electrons repulse valence electrons. And that's going to be a huge concept in chapter 7. Well, these kind of, they come together. All right. So when it says core electrons are harder to remove, that would mean they have more binding. I don't know what, I don't even know what was coming out of my hand right there, but energy. All right. If they're easier to remove, they have less binding. Oh my. It says binding because I say it does. Okay. I'm not dyslexic. My name is Davidson, where a D goes that way and a D goes that way, and it ruined my life. Because then you get to school, you know how to write your name, and they're like, well, B's go this way. You're like, well, oh, it's been a struggle. Like, it's embarrassing. I'm 46, and I still get my D's and B's backwards. Don't get smart on me right now. I don't need logic. I do know one thing. I'm trying to think of my dyslexia joke. If life gives you lemons, make lemonade. If life gives you melons, you may have dyslexia. That's deep right there. Huh? You get it? If you don't get it, write lemons and melons. I don't know.
No, you won't be able to read it.
See, they switched the M and L.
Yeah, see, you're welcome. That's about my only joke I have, so sorry. Okay, here you go. When you see these graphs, I hope that you see them in a way that is a lot like the boxes. Now, you all like this, but I don't really care if you do or not. I get paid either way. Here we go. I'm going to shrink this just for a second and rotate it.
And then, if only you could flip it this way.
Wait, turn it upside down. So it'll be icicles.
Nope.
So,
It's okay. 1s. Oh, whoops, I screwed it up. There we go. 1s, 2, 2s, 2, 2p6, 3s, 2. These lines are literally showing you the same thing that our boxes did.
whoa.
Now, they're horizontal instead of vertical, but we'll live. So here we go. Oh, where did I? There we go. I was about to say, where did I go wrong? And it was when I chose this major. Just kidding. This job's awesome. It is. If that sounded passive aggressive and sarcastic, it wasn't. I absolutely love this job. It's fun. Especially this class. I actually do really like you guys. As an AP class, you like top notch. I enjoy it. Pretty much every year I have a blame, the chart goes off. So, are you the youngest?
No, I'm a middle child.
Oh, sweet. Okay, here we go. Here's what's happening. These peaks are showing you the energies at which electrons were removed. And it took this much energy to remove some amount of electrons. And then it took this much to remove some amount, but they're equal. Since they're equal, and we know each one has 2, And to empty it, we'd have to get rid of both. Then we would know the height of this is 2 electrons. Woo! My cough sneeze. What? Thank you. All right, then this one happens to be 3 times taller. Well, what's 3 times 2?
I think it's
6. So we have 2, 2, 6, and 2. That's a pattern. 1s2, 2s2, 2p6, 3s2. This is element number 12. This is element
I don't know what that is.
Mg. Okay, like from these pictures, we can determine what the element is. You all right with that? What?
If we want to determine
If we wanted to. Now, 90% of the time, these look like this, but occasionally there's one that's only half as tall. And yeah, this is 3s1. Like, don't panic. And it could be here, like it could be that tall. Now that, whatever, it usually isn't, but it can be whatever it wants to be. It's America. Okay, someone tell me right now, actually, don't tell me, I don't even care. Tell your partner why these two took so much energy to remove. All right, now, can we all concur that these two are geniuses?
Yes, we already knew that.
We can. All I'm saying, can we all concur? All right, so they had a great answer that was correct, but it wouldn't be good enough. I didn't actually hear her speak, technically. It wouldn't be good enough to get a 5. You have to include Coulomb's law. Okay. Now, Blaine was right. It has a higher binding energy. Why? Because what part of Coulomb's law? Close. It's the R squared, right? These electrons are much closer to the nucleus, which means the attraction is stronger, which means they have a higher binding energy. So don't forget to include that Coulomb's law. We're either going to mess with the distance or we're going to mess with the charge. You okay with that? Those are the things that matter. All right. And when we do these, we're usually talking about the distance. So the ones in the 3s2 were the easiest to remove because they are the farthest from the nucleus, which means R squared is now really large compared to what it was before, right? So we have a smaller force. Tricky, just make sure you include Coulomb's law, because that's like the standard on the AP test includes Coulomb's law. All right, so yada, 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 yada. Good enough. Whoa, I feel like we did that. Okay, so here we go. Oftentimes they will want you to compare things. All right, so we have beryllium, we have magnesium. I don't know what the question would be here, but let's see, we got a peak here of 1s2 and it's at 100 versus here is 1s2 and it is at 10. Answer, explain, if you would, using this with your lab partner. Why is this one so much higher than this one? Ready, set, go. You said it, you just don't know how to put it in there. So that's good.
I just did it.
You done did it? Okay, here we go. 3, 2, 1. We ready? All right. Because of Coulomb's law. All right. What's the main difference? I heard this word a lot. Protons. All right. This nuclear charge is basically a +12. Now, in the next chapter, it's going to be a 2, but just go with me. Okay, it's a +12. There's 12 pluses pulling versus beryllium is at 4 without looking over my shoulder. Yeah, okay. Sometimes I get BE and BO backwards. Nope, no BO. All right, that was a stupid dad joke. Okay. All right. So what we have here, if we want to explain it using Coulomb's law, we would say the nuclear charge of magnesium is greater than beryllium, which causes 12 times 1 to be 12 times stronger instead, well, not times, but 4 times 1 would be the other. So it's 3 times the force of attraction. So when we change the charge, we change one of the Q's. So we just say, since magnesium has more protons, the force of attraction is greater. That's all you got to say. You okay with that? Okay, why did this stay 1 and not 12 and 4? This one is referring to the outer electron. This will be a 1 in this all the time. Okay, here we go. We got these, you did them, right? These are in the videos. So here we have this. Just real quick, what element do you think it is? Nah, is correct. Sodium. Good. Draw an X above the peak that corresponds to the orbit with the electrons that are on average closest to the nucleus. So we'd put an X right here, correct?
Yes.
All right. Because remember, it isn't really, like the nucleus isn't on the graph, but it's basically here. All right. Justify in terms of Coulomb's law, you would say something about the binding energy, meaning it has the greatest force of attraction. We okay with that? Okay, based on the spectrum, write the complete electron configuration of the element. Super easy. 1s2, 2s2, 2p6, 3s1. On the graph, draw the peak corresponding to the valence electrons of the element that has 1 more proton. And I got this wrong the other day, right? I forgot a part. Abby, okay, maybe not.
Wait, what?
We did this together, and I'm like, oh yeah, I forgot that part.
Oh yeah, where it's like before.
All right, so we should have, oops, here, right? It should be 1 more, but it would be shifted a little bit that way, because instead of 11 protons, the one with 1 more proton would have 12, which would pull this a slight bit more. With me? What?
Why didn't it pull the other one?
Well, it would. It just didn't ask me to do that. It just said to draw this one.
Numbers for this, like replace it.
No. Nope. You will. These are always like exactly this. You have the graph. It wants the configuration, and then it will test your knowledge of Coulomb's law in some way. So the knowledge of Coulomb's law on this one was, if you add a proton, it will shift this left. Yada, yada, yada. Those are the answers. Oh, I showed the answer here. The PES, Photoelectron Spectroscopy data for 1s sublevel of lithium and 1s sublevel of sodium represented blah, 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 blah. Do you agree with the claim? Justify your answer in terms of Coulomb's law. So a student claims that element A is lithium. Do you agree with the claim? No. The answer is no. What's that? All right. Now, I don't know if I heard you right, but I swear someone said there's only 1 blue line. Well, that's true, but they're only showing the 1s, not all of it. But lithium has less protons, so it would have a lower binding energy.
Thanks.
Sodium has more, so it would have a higher binding energy. Easy enough? Okay.
Man, I've never felt so confident in a topic in this class.
Okay. This, go ahead.
You said you struggled.
This one right here. This was on the quiz? Okay, you're welcome.
No, I just gave up after I got to the airport.
Calculate the wavelength in meters and nanometers. Whoa, that's just hideous. Who does that? I don't want to do this. Of the electromagnetic radiation needed to remove an electron from the 3s shell. So which one is the 3s?
The fourth one up. Yeah, that one.
Right here, right? So we have 7.1 times 10 to the negative 18. That's joules, right? And I need wavelength. I have a E equals hc over wavelength, correct? Algebra says that wavelength then is equal to hc over E. You okay with my algebra there? All right. This is the value for E, even though my E looks weird. All right. And H and C are constant. So 6.63 times 10 to the negative 34 times the speed of light in nanometers. Good. Divided by 7.1 times 10 to the negative 18. Now, we can do it in meters. We just change this to the 8. Nanometers is what? $28.01. Anyone back that number up?
Yeah.
Okay. So if we had light at 28.01 nanometers and we shined it on, does it say what this is? I don't know, whatever. We got three. So that's calcium, right?
Yeah.
All right. So if we shine this wavelength of light on calcium, we could eject one of the 3s electrons. Now, we don't have that light, like that's out of our view. That would be like ultraviolet. But does that make sense? Okay. Look at that right there. What does it mean? Now, by drawing that arrow, I just destroyed it, but that's deep. Existential crisis mode activated. All right. So that's the correct way to write it. Okay. So now we review. Whoa, review. What's that? That is all you need to know for the exam. Yes, for those exceptions.
Do I have to know the number?
Any exception.
Yeah. Greek.
Anomaly. I have no idea how to spell it.
You don't give us any numbers, do you?
What?
Like the.
I'll give them to you.
Like the nanometer one too.
I will give you the constants. Yep.
No, I didn't figure it out.
All right, here we go. 1s, 2s, 2p, 3s, 3p, 4s, and then what? 3d. All right, so the exceptions, once again, all these are full, right? So the question then is up here. The exception says, if I have 1, 2, 3, 4, 5, 6 electrons, they don't pair up this way. One of the S is promoted and put in right there. And then one of them disappears.
Oh, I just choose random letters?
And so what would happen here, or which ones are they? They were MO, CR. Is that the one above MO? What's under MO? Tungsten. One more. OS. SG. Oh yeah, Seaborgium, one of the cuter names, named after like something Seaborg. I can't remember his first name. Yeah, this one's radioactive, so we don't really do configurations for radioactive things all that often, but it's fine. So these things here, their configuration would be S1D5. Now, it also works when we want to fill this up all the way. And that would be your silver, copper, and gold. So 6.26102 times 10 to the 23rd. Are we okay with those exceptions? All right. Well, hold on. Whoa, I want to erase all of that.
So wait. H times C. This is life changing. And I can leave all my program stuff into my calculator when I do Nanometers.
Yeah.
Holy mashed potatoes! It's a miracle.
Okay. Look at what we've done in our notes. This is absolutely on the exam.
Well, variables have many different words, Preston. I think that's not
Oh man.
I can write sentences. What's the best way to say it?
All right. Let me give you some test tips here. You ready? These are not the answers, but I will be giving you the reaction or the equations you need. One is that E equals HV. One is E equals HC over lambda. From these two equations, you can answer these questions. So when in doubt, look at the equation. So there's a relationship here between E and frequency. Is there a divisor involved? No. If I'm not dividing, then E and frequency would be directly. Because if V is bigger, E is bigger 100% of the time, right? All right, in this one, there's a relationship between E and wavelength, correct? Are you dividing? Yes. So E and wavelength are inverse. You got it? Oh, much better. Are you okay with that? Okay, so now we have lambda and frequency. I don't even know what to do here. They are directly, no, inverse. I don't give you this one, but c, the speed of light, is equal to lambda v, which means v or lambda, either one, is equal to c over the other one. This is supposed to be the v. So they would be inversely related. You know how you could tell that without this one? In this equation, v is on top. In this equation, lambda is on the bottom. So they have to be opposite or inversely related. Okay, this is on the exam. It's a couple sentences, and it says energy is, and then there's a blank related to whatever and whatever. You with me? All right. Okay, let's see what else we got here. So you'll start off, it asks, give the full electron and noble gas configuration of the following elements. And you have to do 1, 2, 3. 1 is really simple. 1 is medium and the other one is medium. The biggest one has a few, but it only asks for the short version of that one. Then it says electromagnetic radiation with a wavelength of a certain number. I'll make it up. All right, appears as a certain color. We'll just say blue. All right, to the human eye, the frequency of the light is blank. What? So how are they related? C equals lambda rho. So rho is equal to C over lambda. You did it in like 5 seconds too, right? So would you like to bear your testimony about programming your calculator?
Guys, this has changed my life for the rest of eternity.
Program your calculator, because then you just go boom /420 and you're done. Program your variables. Okay, so what do we end up with? Abby, what'd you get?
I got 7.1 to the 14th power.
To the 14th.
Yes.
All right, and that would be what unit?
That's a good question. I don't know.
S to the -1. It's on the test anyway. It just says blank. And S to the -1's already there.
So for storage,
Okay. This one's a little different. This is like the question we did that Davis said he struggled with on the quiz, and definitely more than him did, I'm sure. It says that you have an atom and it has an electron, and it says to eject it took a certain amount of energy. And I'm going to say it takes 541 kilojoules to remove it. What's the longest wavelength of light that can be used to eject it from the metal? So wavelength, what equations do we have with wavelength and energy involved? E equals, whoops, that's not what I want. What am I doing? I am like, whoa, There we go. So I would solve for what? It wants lambda, right? So lambda equals hc over E.
Oh, I did wrong.
Now this is a trick question. What's wrong with it? It's in kilojoules. So you need to make sure that you have 541,000 joules. The reason why is because the unit of H is in joules. Right, Carly? She knew. She had no doubt. All right, anyone have me a wavelength yet? Anybody? Ooh. Is that right? Someone else have that number?
Wait, sorry. Yes, that's what I got.
Okay.
That's what Preston got.
Okay, sound fun? I didn't read a word that's kind of important here, but don't worry about it. Like it's good enough, but it's that process. We okay with that? Okay, let's see. Whoops, I can't do that. This is a question, we better read it now. Oh crap. How many subshells are in the fourth shell? Why 3? All right, right here, the fourth shell means the fourth row. S's, D's, and P's. There's 3 of them. So like it's an easy one. It's just like, if I never told you, you're like, what?